what's going on. It's not recording. There we go. Okay. All right, so let's start with the homework. So you had to find some coterminal angles, right? So remember, depending on what we're dealing with, if we're dealing with degrees, we can either subtract or add 360 degrees. If we're dealing with radians, we can either add or subtract 2 pi. All right, so that's essentially all you had to do. So for number 1, we had to find an angle that is coterminal with 135 degrees. All right, so I'll show you both. So either you can add 360 or we can subtract 360. And where's my calculator? All right, so 135 plus 360 would get you 495. All right, so 495 is an acceptable answer. Or we can subtract 360 and we get negative 225. And so both of those are acceptable solutions to coterminal angle with 135 degrees. Okay, any questions there? All right, for the second one, I wanted you to find 2 angles coterminal with negative 315. So I'm going to add 360, right, because we got a large negative number. So I want to stay away from even larger numbers, so I'm going to add. So there we get 45 degrees. Okay, now we didn't do this yesterday, but I can keep adding 360 and I'll still end up at the same spot. So I could do 45 degrees plus 360 and get 405. And that is also going to be coterminal with the 45. Okay, you could have subtracted 360 as well. And that would get you negative 675 degrees. All right, and if you subtracted first and you wanted to subtract again, you could subtract from there. And that'll get us negative 1,000 something degrees. All right, but we like to keep it simple. So I would have done those 2, but if you gave me any 2 of those 3, you would be good. All right, any questions about the degree part of coterminal?
So it's always
when we were talking about coterminal, yeah, always 360. If you see complementary or supplementary, then it changes between 90 and 180. Okay.
Oh, that's why I got confused.
Yeah, I think I saw one. Some of them you were on the right track, but yeah, I think you're number 1. I saw you did what, 180?
Yeah.
Okay, yeah, so just be careful. All right, yeah, so these are all coterminal. All right. Now for the radian part. Our first, number 3, we had find an angle that is coterminal with 5 pi over 2. All right, so I'm sorry I didn't upload, a fancy version of that, so I just wrote 5 pi / 2. All right, so hopefully that didn't confuse you. So remember, we have to add or subtract now 2 pi. So that 2 pi is going to change to 4 pi over 2, right? For a common denominator, 2 pi becomes 4 pi over 2. So one of your solutions might have been 9 pi over 2 if you added them, okay? Or if you subtracted, you would just get pi over 2. Right, so either of those would have been an acceptable answer for number 3. All right, and if you think about it, okay, 5 pi over 2, well, that's greater than 2 pi. right? So 5 pi over 2 would be one full rotation and then a little extra, right? Well, that little extra is pi over 2, which is 90 degrees, okay, if we convert it back. All right, so the 5 pi over 2 would be the 360 plus another 90 degrees, which would be 450. Right, and then number 4, I'm running out of room here, so I'm just going to go back up here. Okay, number 4, again, I asked for 2 coterminal angles with negative 3 pi over 4. All right, so again, I'm going to add, and I'm just going to do the conversion right away. All right, so 8 pi over 4 is 2 pi with a denominator of 4. So when I add those, I get 5 pi over 4. I could add, so that's one solution. I could add another 8 pi over 4, and I would get 13 pi over 4 there. Okay, you could have also subtracted 8 pi over 4 from the original. All right, so negative 3 minus 8, be careful with your signs here, is going to be negative 11 pi over 4. All right, and again, you can, if you did this first, and you can subtract another 8, and you get negative 19 pi over 4. All right, so these are all acceptable answers. Now, honestly, you could have kept adding 8 pi over 4 until you got to a ridiculously high number, and it'd still be a coterminal angle.
Mr. Murray,
What's that?
Barbara said that her internet isn't allowing her to stay in class.
Okay, all right. Thank you for letting me know.
No problem.
Any other questions? All right. So for today and tomorrow, before we get into the actual trigonometry part with sines and cosines, we're going to take a little look at circles, right? Because part of this, we're talking about rotations, right? And when we rotate, it's just natural that we end up with a circle, right? That's the form that we make when we rotate things. So first, we're going to talk about arc length. Let me get rid of this. We don't need this anymore. Oh, that's a crummy circle. That's a little better. All right. So we're actually what we're talking about today is a little physics. All right, but before we do that, we got to talk about one thing, and that is arc length. So arc length is the measure, a partial measure of our circumference of a circle, right? So here we have a circle with radius r. And again, remember, that angle in the middle we call a central angle, all right? Now, to calculate this, we need our central angle in radians, okay? If this was degrees, we'd have to go through the whole steps of finding the circumference of the circle and then doing a proportion. And that's how you might have learned it in geometry. Like I said, it's probably been a while since you've seen something like this. I used to teach geometry, but I know they changed some things since when I taught it. So I'm not sure how far you got into things like this. So actually, to calculate the arc length with this information, our central angle is pretty simple. Okay, so then what happens is the arc length that we say that is covered by our central angle, right? So that central angle is telling us what part of the circle we're looking at. Okay, well, that's just going to be S equals the radius times your central angle. Okay. Now, you may not be given the central angle in radians. You may be given it in degrees. So remember, to calculate, we went over this either yesterday or Monday, possibly. Okay. We can get it from over here, right? So you take those two are directly related, right? If I solve for S here, I would multiply by the radius. Yeah, let's do one quick example. Okay, so here we're given a circle with radius 4. Our central angle is the larger angle here, 240 degrees. So the way you might see this, let me word this correctly. Right, so when you, moving forward, you might see it worded like this. Okay, so they might say, find the length of the arc intercepted by the central angle of 240 degrees. Right, so that intercepted comes from the fact that we extend our radius to meet with the circle, right? So we're finding the length of the line that goes from this point around the circle 240 degrees to this point. Right, so again, the first thing that I want to do here is get that angle to radians. Right, so we're going to take our conversion units. So I have 240 degrees. Right, so we're going to multiply that by pi radians over 180 degrees. So here we're going to have 240 pi over 180. All right, so I want to reduce the 240 over 180. They are both divisible by 60. So when I divide 240 by 60, I get 4. When I divide 180 by 60, I get 3. All right, so my central angle of 240 degrees is actually 4 pi over 3 radians. So now we're just going to use our formula. Okay, S equals radius times your central angle. So when we have this question, now this is usually up for debate, how they want their answer. So if I just multiplied, we would get 16 pi over 3. Now, we have a slight issue here. This is whatever units they give us for the radius, right? So let's say that's inches. Now, this is in radians. Now, we don't really have a way to combine inches and radians, right? But we're looking for the measure, not of an angle, but of part of a curved line, right? So the radians only applies to my angle. So the units of the arc length are going to be whatever your units of your radius are. When we do that, if I'm not talking about actual degree measurements, we don't like to have the pi in there. So, for a basic question that I'm asking you, okay, if you gave me this answer, you wouldn't be wrong. But moving forward on, an exam or something, if it's, especially if it's like multiple choice, you might not see this pop up, right? So you would calculate that. And usually we round to 2 or 3 decimal places to be as accurate as possible. So I have 16 times pi. And then we're going to divide that by 3. All right. So we're going to say that our arc length is about 16.76. Okay, and again, our arc length is always in whatever units. Okay, thank you, Barbara. Yeah, you can, if you have troubles, you can just go back and watch the videos. Okay, any question about arc length? Okay, so now I don't want to spend too much time on this. It is good to know, but really we need this to move on to the real topics that we're going to talk about today and tomorrow, and that is when I say speed. Okay, I'll say speed. Okay, linear and angular speed. I guess that's pen. Oops. Okay, so when we talk about circular motion is pretty interesting in the physics world. So anytime we have circular motion, whether it's a tire spinning, I don't know if you've seen in like medical shows when they're testing blood samples and they're spinning, that's called a centrifuge, things like that. To larger scale things like the orbit of the moon and the planets around the sun, circular motion, we see a lot of it in nature. Now there's 2 parts of circular motion. Okay, and those 2 parts are the linear and angular speed. Now, angular speed is, just going around in a circle. How fast are we actually spinning? Linear speed has to do more with the actual physics. Now, most things like to go in a straight line. Okay, all of Newton's laws, most things like to stay at rest until they're acted on by an outside force. And then once an outside force acts on it, usually it goes in one direction, right? You have a pool ball sitting there, you hit it with another pool ball, it goes in a straight line. That straight line depends on what angle you hit it. I'm not going to get into the physics of playing pool, but I think you get the idea. With circular motion, we have other forces at play. Now, depending on what we're doing, if I'm talking about a tire or something physical, okay, that tire is connected to the middle, right? There's this kind of force that's pulling it in, and that's built in. If we're talking about something like planetary motion or the moon going around, okay, this inward force is gravity, right? If I have the moon circling around, okay, it keeps circling because gravity's pulling it down. Not down, but in. Anything moving in a circle wants to go in a straight line. But again, something pulls it in. So at each one of these points, at any point, okay, if you let go somehow, right, whatever is moving in a circle will travel in a straight line. I don't know if you guys are familiar with the story of David and Goliath, but David had a slingshot, right? And that's how he took down Goliath, right? He was using angular speed, right? You have a rock at the end of a string. You whip that string around a lot. You build up a lot of speed, a lot of momentum, and then you let it go in a straight line, okay? That's what's going on here, right? So you're spinning it around, spinning around, spinning around. You let go, and wherever it is, it travels. And now I'm going to throw another word out here that's tied into everything, in a tangent line. Okay, so hopefully you remember tangent lines from geometry. Right, if we have a line that touches the circle only at one point, okay, that's our tangent line. So the linear speed, okay, a lot of times we talk about, I want to kind of move away from things like tires because, I mean, you know, they do move at an angular speed, but it's kind of hard to grasp the concept of a tangent line with a tire, right? So I like to bring it back to planetary rotation, right? So for some reason, right, this is the Earth circling the sun or the moon circling the Earth. For whatever reason, if we lost all gravity, something happened and gravity didn't exist anymore, then wherever we were around the sun, we just start going off in that direction forever, okay? Right? Depending on our position. All right, so tomorrow we'll take a look at the actual math of this stuff and how to calculate them and the relationship between the angular and the linear speed. All right, so quick, simple homework tonight. I'm just going to ask you to find the arc length of something. All right, and then tomorrow we'll get further into our linear and angular speed. Any questions?